I am Maddie Rapaski, and I will be presenting on the ECG device that I developed this semester. The goal of the project was to create an ECG device with a digital display. After doing some work with an LCD display, I decided to switch to making an Android app that would be compatible with the device. After creating a device that would be able to accurately input analog data, I needed to perform signal processing to clarify the sinus rhythm and give a clear output to the user. In order to avoid a conflict with the Institutional Review Board at CSU, I decided to use simulated data instead of human subjects. This data was collected from PhysioNet, which is an online database that has a wide variety of samples from human subjects and are published for free use. I used an Arduino Zero to convert the data from PhysioNet to an analog signal. In order to have a functioning program, I needed to load the heart signal onto the Arduino Zero so that it was outputting a physical signal that would easily simulate the heart signal. I also needed to load the program onto an Arduino 101 and start the ECG app on the Android device. I generated the Android app, by using the PFOD design app. This PFOD design app allowed the designer to create a general layout for the app, including color schemes, buttons, and formatting, and output a working code based on that template. Taking this template for the Arduino 101, I was able to elaborate and add the filters and data processing that I needed for this project. The signal processing consisted of a few filters. The first filter I tried was a simple moving average filter. This didn't give the best results. As shown in the graph, there's not a very clear periodicity to the signal, as well as any signs of the local maximum and minima are completely erased. So this was not a very good result. The second filter I used was the cumulative moving average filter. Over time, this simply took the average of all the data points and ended up not giving a good result at all. So there's obviously no clear sign of periodicity and no local maxima or minima to indicate any normal sinus rhythm. The exponential moving average filter was a little bit closer to what I had intended this to look like. The data shows clear signs of periodicity, however the local maxima and minima are not defined, and there's no clear sign of the sinus rhythm that I had been looking for. The Raymer-Douglas-Pucher algorithm was more precise than the exponential moving average filter. This filter did show signs of periodicity and occasionally captured the maxima that the data contained. However, there was not a consistent output of sinus rhythm, making this not the best choice. The Kolmogorov-Zerbenko algorithm was closer still. This algorithm showed clear signs of periodicity as well as maintaining the local maxima and local minima. However, there was too much noise in the middle to define the definitive sinus rhythm of the sample. I also tried using a custom bandpass filter in order to try to isolate some of the noise specifically and cut it out. This filter was intended to cut out very low frequency noise, particularly the AC noise around 60 Hz from the power supply, and as well as high frequency noise that was caused by movement of the electrodes on the patient. However, it did not give a very clear sign of the local maxima and minima where it did maintain the periodicity. After the semester, I did come up with several results. In order to connect to the Arduino 101 from the Android device, the devices needed to be paired. After they were paired, you could launch the PFOD app and connect to the Arduino device. Connecting to the Arduino device happened by searching for the Arduino device name and allowing it to connect by BLE automatically. Once the Android device was completely paired to the Arduino, the start menu for the program would automatically come up. After selecting the start button, the filter selection menu was displayed. Selecting any one of the 6 filters shown would bring up a live graph of the data, some of which you've already seen in previous slides. Each of the graphs was limited to about a 2-second window, moving the data fairly quickly without causing any unneeded condensation of the data. After some research, I found that the delay of the Bluetooth caused almost a similar effect to a low-pass filter. This was able to eliminate some of the noise and provide the results that I wanted. The video on the right shows the working result that I have. As you can see, there is the local maxima, which indicates the QRS complex, as well as the P wave, which can be seen as the slightly smaller maximas beside the obvious maxima. Although there is a bit of noise, you can clearly see the sinus rhythm within that noise. When compared to the oscilloscope reading of the analog output, it's clear that there's still some work needed, and these differences can likely be attributed to suboptimal settings of the Bluetooth. I was not able to fully experiment with the Bluetooth settings in order to find the optimal baud rate for the data transfer to work completely. There are some future extensions that I'm planning to make. I'd like to refine the filtering process to reduce the noise. This will give a clearer output for the users. I'd also like to add a GPS module for the device tracking during use. This will allow the user to track any outdoor runs or workouts that they use this device during. And I'd also like to calculate the heart rate. I tried over the course of the semester to use built-in BLE services that could automatically calculate the heart rate. However, there was some interference with an existing BLE service that I needed, which ended up making it impossible to connect the Arduino 101 to the Android device. Therefore, it would be necessary to manually calculate the heart rate and display it separately. Thank you very much.